This is a review of homework 9. So number 14 said for each of the following studies, decide whether you can reject the null hypothesis that the groups come from identical populations. This is part A. There's also a part B. For the most part, the numbers are the same in terms of the mean and the estimates of population variance. The only thing that's going to change across these two problems is the sample size for each group. And so we're going to look and see how that sample size, so all else equal, we are going to look and see how sample size affects the size of the F ratio. All right, so just recall that what we want to do with an analysis of variance is calculate our F ratio, which is the ratio of variance between groups to the ratio of variance estimated using the within groups approach. And so the first thing we're going to do is get an estimate of population variance from the variation of scores within each group. And so to do this, all we have to do is take the simple average of the estimate of population variance that we've gotten from within each one of our groups. And so there's our formula. Again, we're just going to take the simple average. And so doing that, we get a pooled estimate of variance, S squared within, which is 5. Next thing that we're going to do is estimate the population variance from the differences between group means. This is a two-step procedure. We're first going to estimate the variance of the distribution of means, and then we're going to use that to then estimate the population variance. So the first part is to estimate the variance of the distribution of means. We're going to treat our three means as a little mini sampling distribution, a mini distribution of means. So the first thing that we need to do is, there it is, we need to calculate our grand mean. So 12 is just the average of 10, 12, and 14. That's the overall or grand mean. Then what we're going to do is we're going to get the variance. And so we do that by looking at the squared deviation of each mean from that grand mean. Okay, so we're going to take the squared deviation, we're going to take the sum of the squared deviations, and then divide that by degrees of freedom. So that gives us basically an estimate of the variance of this distribution of means. So doing that, we get an estimate of the variance of the distribution of means, which is 4, and then we can work backwards to get population variance once we know that. So we do that by multiplying the variance of the distribution of means, S squared m, by the sample size, okay, and then that gives us an estimate of population variance, which is 20. So our F ratio is just our estimate of population variance that we determined using the between approach divided by our estimate of population variance that we figured out using the within approach. So we get 20 divided by 5 is 4. So how big does our F ratio need to be? We of course need to compare the F ratio that we calculated to a critical value. We determine our critical value using degrees of freedom between groups. In this case, we had 3 groups minus 1 is 2 degrees of freedom. We also need our degrees of freedom within. Our overall degrees of freedom within is the degrees of freedom within each one of our groups. So degrees of freedom 1 plus 2 plus 3. So we had 5 people in each group. That's a degrees of freedom of 4 within each group. Summing that together is degrees of freedom is 12. So we're looking for a critical F value that is based on 2 and 12 degrees of freedom. And so looking that up in our table of critical values, with alpha at 0.05, we get a critical value of 3.89, and that's how we do. We find it in the table. So recall that the between groups degrees of freedom is in the numerator, within in the denominator. At 0.05, we've got a critical value of 3.89. So we determine whether to reject the null hypothesis, and because our F ratio of 4 is more extreme than our critical value, just by a little bit, we are going to reject the null hypothesis. And by rejecting the null hypothesis, we're concluding that the means are drawn from populations whose means are not identical. Okay, so if the null hypothesis is that mu1 equals mu2 equals mu3, we're going to reject that null hypothesis. And what we can say at this juncture is they're not drawn from populations with identical means. Okay, so basically the same problem, but the only thing that changes in part B is that the sample size is bigger. The means and the estimate of population variance is the same. So really this first step, we don't need to do anything different. It's just pooling together our estimate of population variance, and so the sample size doesn't come into play for this particular calculation. So that number is the same. The other thing that's the same is our estimate of the variance of the distribution of means. Okay, so that's the same. The only thing that's different is that in doing the second part of the process for figuring out the variance of the population variance using the between approach, we're just going to substitute in 10 where we had 5 here before. And what we're going to see is that gives us a bigger estimate of population variance. So then when determining the F ratio, instead of having a 20 here, we've got a 40. So our F ratio goes from 4 to 8. So really all else equal, with the same amount of difference between the three means and with the same estimate of population variance using the within approach, we can see that having a larger sample size will produce a larger F ratio. And what this F ratio is telling us is, in a way, it's even less likely that these means, these sample means, were sampled from populations with identical means by chance. Okay, it's like even less likely because of the higher n. Because our sample mean is based on more observations, 10 versus 5, it's kind of even less likely, it's even less probable that we would get these mean differences due to chance. That's what that higher F ratio is telling us. Because the higher the F, the less probable it is that you would get an F that large due to random chance. Okay, so there's a specific probability that is associated with an F of 8. There's a specific probability that is associated with an F of 4. And the probability of getting an F of 8 is even less than the probability of getting an F of 4. Okay, and that's because there's less of a chance that those means are sampled from populations with identical means when you see these differences, and those sample means are based on 10 observations instead of 5. So that's what this example is meant to illustrate. All right. Oh, the one other thing too is that we shouldn't forget to update our critical value. The degrees of freedom between is the same, but degrees of freedom within needs to be adjusted based on the new sample size. So with the new sample size of 10 for each group, degrees of freedom within is 9, so we've got 27 degrees of freedom within, okay? And so we will have a lower critical value. All right, and so we're definitely going to reject the null hypothesis in this case. All right, let's move on to the second example, or the second problem. An organizational psychologist was interested in whether individuals working in different sectors of a company differed in their attitudes toward the company. The results for 3 people surveyed in development were 10, 12, and 11. For the 3 in marketing, 6, 6, and 8. The 3 in accounting, 7, 4, 4. And for the 3 in production, 14, 16, and 13. Higher numbers mean more positive attitudes. So the question is, was there a significant difference in attitude toward the company among employees working in these different sectors of the company at the alpha 0.05 level? Use the steps of hypothesis testing. So the first step is to restate the question as a research hypothesis and a null hypothesis about populations. Arbitrarily, I just went in order: population 1 development through population 4 production. The null hypothesis is always that mu1 equals mu2 equals mu3 equals et cetera, et cetera, et cetera. So we had 4 means. Null hypothesis, those means are equal. Again, at the population level, mu, not sample mean m, but mu. Those means are equal. Alternative hypothesis, otherwise known as the research hypothesis, the population means are not the same. So that's what this overall or omnibus analysis of variance is going to help us determine. That either this is the case and we don't have sufficient evidence to rule this out, okay? So even though we see a little bit of variability between the sample means, there's not sufficient variability among the sample means to rule out that they were sampled from populations with identical means, or there is sufficient variability between those means. Those sample means are so different from one another, that is, there's so much variability among those sample means that it would lead us to this conclusion. We'll reject the null and say that the population means must not be the same because there's too much variability among our sample means to conclude that the means are the same. Okay, determine the characteristics of the comparison distribution. It's going to be an F distribution. In this case, we have 3 and 8 degrees of freedom. Degrees of freedom between with 4 groups is 3 because 4 minus 1. Degrees of freedom within is going to be 8. We just take the degrees of freedom from all 4 groups. There was 3 employees in each group. 3 minus 1 is 2. Adding up 2, 2, 2, and 2 for the 4 groups, we get degrees of freedom. That is 8. So there's our F distribution. So we're going to determine our critical value. We do that based on 3 and 8 degrees of freedom at an alpha level 0.05. The critical value ends up being 4.07, and we get that from our lookup table. Okay, so now to determine our F ratio, we've got 3 overall calculations to do. We got to determine the within groups variance, the estimate of population variance based on the within groups variance approach, the estimate of population variance based on the between groups approach, and then we're going to calculate the ratio of those 2 variance estimates. Okay, so in this problem you were given raw data, and so several of our previous problems you didn't have this raw data and you were just started with the estimate of population variance. So I really like this problem. It's a little bit more time consuming to do, but it's really reinforcing where the numbers are coming from. So all we're doing is we're taking the 3 employees or the 3 participants in the development part of the company. Here's their scores. We calculate the mean among these scores, and then we're going to calculate the variance. So we do that using the same old approach that we've been using all semester, which is to take the deviation of each score from the mean, square that deviation, take the sum of the squared deviations, and then we're going to divide by degrees of freedom, 2, not n, which is 3, but by degrees of freedom because we're getting an estimate of population variance. If we were just interested in getting the variance and the standard deviation of this particular sample, we just divide by 3. That would be a descriptive statistic. But what we're doing is we're getting an estimate of population variance, and we need to correct that estimate because it would be too small otherwise, so we're going to correct by divided by degrees of freedom. So our estimate of population variance is 1. That is, we believe that these participants are sampled from a larger population of all the employees in development, and we think that the variability among all development employees is 1. We do that same thing for our 3 participants in the marketing department, exact same approach by calculating the mean and then figuring out the estimate of population variance by taking the sum of the square deviations and dividing by degrees of freedom. So I've just repeated this approach for then accounting and production. So this gives us the data that we need to now work with to be able to carry out our ANOVA, because we have sample size for all 3, we've got our mean, or we've got our sample size for all 4 groups, we've got our mean for all 4 groups, and we've got our estimate of population variance for all 4 groups. So the first thing that we're going to do is figure out the within groups estimate of population variance, and all we have to do is take the simple average of 1, 1.33, 3, and 2.33, and then divide by the number of groups, which is 4, and we can just take this simple average because the sample size in each group is the same. If the sample size was different in each of our groups, we would have to weigh this estimate based on the sample size in each group. But in this particular class, we're just going to keep the calculations simple because it's more or less to show you the conceptual basis for the statistic. In reality, for statisticians or for researchers or for people in organizations that want to carry out an ANOVA, they're going to use a statistical software. And so this is really just to show you how the statistical software works. This is to give you an appreciation for the statistics. So we keep the calculations a little bit easier. Okay, so that's one simplifying thing that we're going to do is we're just keeping sample size the same. All right, so that is our estimate of population variance using the within groups approach. We're then going to use our between groups approach to figure out population variance. First thing we're going to do is estimate the variance of the distribution of means. Okay, so we calculate the grand mean. So 9.25 is just the average of 11, 6.675, and 14.33. We take the deviation of each mean from the grand mean, square that deviation, and then we add up all those deviations and then divide by degrees of freedom 3. And then we have one more step, which is that we've just figured out the variance of the distribution of means. Oh yeah, there we go. So I had to finish up my calculation there. So we get that the variance of the distribution of means is 17.86. And so that's the variance of the distribution of means. It's not the estimate of the population variance. We have one more step. We need to multiply the variance of the distribution of means by the sample size, and that gives us an estimate of population variance, which is 53.59, using this between approach. Okay, so then we calculate the F ratio as the ratio of S squared between over S squared within, and we get an F of 27.91, which is way larger than our critical value. Okay, so we're going to reject the null hypothesis. We can conclude that the differences observed between these group means are greater than the differences expected by chance if all samples were drawn from populations with identical means. So therefore, we reject the null hypothesis that mu1 equals mu2 equals mu3 equals mu4. Okay, but we don't exactly know which means differ from which other means. That's the kind of the next part of the problem. Okay, the only thing that we're able to conclude right now is kind of a generic conclusion that individuals working in different sectors of the company differ in their attitudes about the company, but we're not able to say specifically how yet without doing our simple comparisons. Sketch the distributions involved. I'll look to see what you did in your homeworks, but it's kind of hard to replicate this in the PowerPoint, but just see the examples that are in the chapter for that. Figure out the effect size. Our effect size in ANOVA is R squared. R squared tells us the proportion of variability that is explained by group membership. Okay, so I should say the proportion of variability in our outcome measure that is explained, aka accounted for, by group membership. So that's determined using this formula, where all we need to do is plug in our estimates of S squared between and S squared within with degrees of freedom. The most important thing is interpretation. This R squared can range from 0 to 1. If you calculate an R squared that is less than 0, you've done something wrong. This statistic, based on the formula, can never be less than 0. It can also never be more than 1. So if you get an R squared that is outside of the boundaries of 0 and 1, then there's a calculation mistake. Okay. So what this R squared of 0.91 tells us is that we can explain 91% of the variability in positive attitudes by knowing something about which sector of the company employees work in. So we can explain nearly all the reason why those attitudes are different by merely knowing which sector of the company people work. So basically all the variance. That's a very large effect size. Okay, the next part of the question asks you to do plan contrast using the overall 0.05 level with a Bonferroni correction, testing for each of the 5 contrasts, and then it starts with engineering versus production, and then it goes on to marketing, accounting, development, yada yada. I don't know about you, but this engineering versus production was not in the original problem. That seemed to be added. We only had 4 groups in the original problem, so I didn't get that. That was weird. But it does simplify our lives because when using a Bonferroni correction, we're going to divide this alpha level by the number of comparisons that we're going to do. So we're just going to divide this 0.05 by 5, and it ends up being a nice even number, or a nice round number. Okay. All my animations are screwed up. That's all right. So when doing these multiple planned contrast, the idea is that even when predictions are made ahead of time, some statisticians advocate that steps should be taken to control for experiment-wise error. Recall that experiment-wise error is the accumulation of kind of likelihood or probability of making a type 1 error by doing multiple comparisons. So to guard against making a type 1 error, One way to correct for that is to use a Bonferroni correction. It's just a corrected alpha level for each one of your tests or comparisons. And it's determined by taking your original alpha, which is typically 0.05, and then dividing that by the number of comparisons that you're going to do. So in the current example, we're going to pick a critical value of f that is associated with a probability of 0.01, and that's determined by taking our original alpha 0.05 and dividing by 5 tests. So if you go back to the previous slide, you'll see that there was 5 comparisons that we were instructed to do. So we need to then get a critical f that is based on 1 degree of freedom between, because all simple comparisons are just between 2 means. So when we just have 2 groups, degrees of freedom is 1. And then we retain the degrees of freedom within from our omnibus analysis. So we had 8 degrees of freedom within from our omnibus analysis, and we retain that. And then we're going to use a corrected alpha of 0.01. So looking that up in the table, with 1 degree of freedom between, 8 within, a new p-value or alpha level, synonyms really, of 0.01, we've got a critical f of 11.26. So how to figure each simple comparison? What we're going to do is each simple comparison is just comparing 2 means. We're going to use the within groups population variance estimate that we've already calculated, which was 1.92 in this example. So that's done, and that's going to be the denominator of our F ratio for all of our comparisons. So that's done. The only new step is to calculate a new between groups variance estimate using only the 2 means of interest. Okay, so we've got 4 comparisons that we're going to do. We have to do this step 4 times. Then we figure the F in the usual way, which is just that ratio of between groups to within groups variance. And then we already just determined what our new critical value is. So that step is done as well. Okay, so for our first comparison, marketing versus production, what we need to do is figure out the variance between these means of 6.67 and 14.33. So we're going to do that using the same procedure of estimating the variance of the distribution of means. Our grand mean here is the average of 6.67 and 14.33, gives us a grand mean of 10.5. Exact same calculation, exact same formula. Sorry, my animations are all over the place. But we've got the deviation of each mean from the grand mean, square that, so the sum of those square deviations. We're always dividing by 1 degrees of freedom in a simple comparison. So our variance of the distribution of means is 29.34. And then we're going to multiply that by 3 to get our estimate of population variance using the between method. Okay, so very important not to skip this step. It's very common on homework or on an examination that people skip this step and they stop right here. So very important to know that the between groups approach, the first thing that you're doing is estimating the variance of the distribution of means, and then you got to work backwards to get that estimate of population variance. Okay, there it is. And then once that's determined, all we need to do is plug that into our F ratio. We're retaining the same within groups estimate of variance, otherwise known as mean square within. We're retaining that same mean square within, and the only thing that's different is we're getting a new between groups estimate or mean square between each time. So our first simple comparison yields an F ratio of 45.84. That's a huge F, much larger than the critical value that we came up with, which was 11.26. Okay, so let's move on to the second one. Now we're doing accounting versus production. Exact same procedure. Figure out the grand mean, calculate the variance of the distribution of means. Once we've got that, working backwards, getting the estimate of population variance, and then plugging in to get an F. So I went through that kind of fast, but here it is again. Exact same procedure. Okay, we just got our 2 means of interest. We're going to recalculate that grand mean because it's only based on these 2 means of interest. But otherwise, calculate the variance of the distribution of means in the exact same way. And then once determined, calculate the estimate of population variance, exact same procedure, but you'll of course notice that we get a different value. And then we're going to plug that into the F ratio. Again, the mean square within stays the same. So that's our our F ratio based on the comparison between accounting and production. So I haven't done the comparison 3 and 4, but if you follow that same procedure, you should get mean square betweens of 28.14 and 54 when you do comparison 3 and 4. We're always using mean square between of 1.92 for all of these comparisons. And then these are the Fs that you should get within a little bit of like rounding error, or your Fs might be ever so slightly different from this, just depending on how many decimals you kept in your calculations, and that's fine. But you should be in this basic ballpark, like plus or minus, maybe like a 0.4 or 0.5 or something like that. You should be pretty darn close to those Fs if you did things properly. So if you're way off from these numbers, make sure that you go back and try to spot your error. As you can see, all of these Fs are larger than our critical value of 11.26, and so we know that we have a statistically significant difference between all of these sectors. Okay, so we can say, based on the sample data that we have, we can conclude that among all employees that work in these sectors, there would be significant differences between them. Like, just how? Like, what do you mean by significant difference? Like, who has more favorable attitudes? We have to go back and look at the means. Okay, so going back and looking at these means, here they are. What we were able to determine is that based on all of our comparisons, production has a more favorable attitude than accounting. Marketing had a more favorable production had a more favorable attitude than marketing, etc. So it isn't sufficient just to say these are significant differences. It's necessary to say these are significant differences because production has a more favorable attitude than marketing. Production has a more favorable attitude than accounting. Okay. One thing that we didn't test was, I believe, marketing versus accounting. Yeah, so if you could test that on your own and see if you get a significant difference. Doesn't look like it because it means you're pretty close, but that's one that you could test on your own. So that's it for this homework. Hopefully that, if you were able to calculate everything correctly, that this, validates that you're on the right track. If you got off and your numbers aren't quite lining up, please make sure to go back and review the calculations. And again, doing the homework is really meant to illustrate the theoretical concepts, so of kind of the logic of why the analysis of variance works. So on the one hand, this is a math class. It's important to be able to demonstrate proficiency in doing the math and doing the calculations. On the other hand, it's important to understand conceptually, why does all this make sense? So as I'm going through the explanations, please make sure that you're paying attention to and tracking the conceptual explanations as well.